Hey, what's up, dogs? This video is about an interesting paradox in probability theory, the St. Petersburg Paradox. So, we're going to play a game with a fair coin. Here's how it works. I toss the coin, and if it lands heads, you win £2, and the game ends. If it lands tails, I toss it again. Now, if it lands heads on the second toss, you win £4 and the game ends. If not, I toss it again, and if it lands tails on the third toss, you win £8 and the game ends. If not, I toss it again, and you can see how this goes. Basically, every time it lands tails, your prize doubles, and the game stops when the coin lands heads. Or more formally, the number of flips n determines the prize, which equals 2n, £2 to the power of n. So here it is. Here's the representation of it. Obviously, that goes on indefinitely. So that seems like a pretty good game. However, there is a catch. The game has an entrance fee. You have to pay a bit of money to enter the game. And the question is, what would be a fair price to enter this game? What's the maximum amount that you would pay to enter? I expect most people probably wouldn't go above £5 or £6. I mean, that's sort of mine. I mean, certainly not above £20. So, in order to explain the paradox here, I need to go into a little bit of probability theory. We can use probability theory to determine the expected value of an action to help us determine the best course of action. We do this by combining the probabilities and the utilities of the consequences. If I'm thinking about whether to perform an action, let's call it Act A, then I'm going to need to consider the potential consequences, C1, C2, C3, and so on. I'll need to consider what the probability of each consequence is, so what's the chance of this consequence happening, and I'll need to think about what the utility of each consequence is, how good or bad it would be for me. Let's say an act has two possible consequences. Then the expected value of the act is the probability of consequence 1 multiplied by the utility of consequence 1 plus the probability of consequence 2 multiplied by the utility of consequence 2. And this probably seems quite abstract, so let's apply it to a specific example. This example comes from me in hacking. Suppose your aunt offers you a lottery ticket. The lottery has 100 tickets and there is a prize of £90 for one of the tickets. None of the other tickets win anything. So you've got two options. You can either accept the ticket or decline the ticket. Which would be best? Well, let's work out the expected value of accepting the ticket. There are two consequences. First consequence is your ticket is drawn. The probability that your ticket is drawn is 1 in 100, or 0.01. The utility of this consequence is £90. That's what you'll get if your ticket is drawn. The other consequence is that your ticket is not drawn. The probability here is 99 out of 100, 0.999, and the utility is just nothing, £0. So the expected value of accepting the ticket, from this equation here, can be seen here. We plug these numbers into this equation, and we get an expected value of £0.9 or 90 pence. On the other hand, of course, the expected value of declining the ticket is just nothing. And there are no probabilities to worry about here because there's only one consequence. Obviously, if you decline, you just get nothing. So it looks like you should accept the ticket. And you'll notice that this kind of reasoning is something that any rational person will do informally all the time. We're always weighing up the utilities and probabilities of the consequences of our actions. This just puts it a little more formally, right? I mean, if you're at a zoo and you drop £20 into the bear enclosure, and you think to yourself, should I go down there? Should I go into the bear enclosure to pick up the £20? I mean, given you think about, given the probability of being attacked by a bear, given how awful it would be to be attacked by a bear, Given the fact that there's not really much at stake, only £20, and so on, you would presumably choose not to do it. So you weigh up the probabilities and the utilities of each consequence, and that's how we make decisions, at least if we're rational. Now, of course, I should say that this particular example that I've given, we've looked at it from a purely monetary point of view. In real life, there will be other considerations. Perhaps your aunt is extremely narcissistic and you know that she's only offering you the lottery ticket so that you'll owe her a favour later. That may reduce the expected value of accepting the gift. On the other hand, maybe she's just a really lovely person and refusing the gift would hurt her feelings, which would mean that the expected value of refusing it would be negative. It would be it would be worse than nothing. So in real life things are a little bit trickier, but this at this point shouldn't affect the statement of the St. Petersburg Paradox. Okay, so now let's say that you're offered the chance to buy the lottery ticket. Let's suppose that your aunt is quite stingy. She demands that you pay £2 for the ticket. Would that be a fair price? We can work out whether this is a fair price by thinking about the expected value of buying it. So in this case there are two consequences as before. So one consequence is that your ticket is drawn. Again, the probability of its being drawn is 0.01. The utility is £90 minus the £2 that you spent on it, so it's £88. The other consequence is that your ticket is not drawn. That's 0.099. The utility is you get nothing, but again minus the £2 that you spent. So that gives us this equation. And the result is that the expected value of buying the ticket for £2 is minus £1.1. And that suggests that you'd be at a disadvantage by paying £2. It seems like your aunt has kind of ripped you off. You're going to be worse off for paying £2. So earlier we noted that the expected value of accepting the ticket for nothing is 90p. What if we paid 90p for the ticket? Well, in that case, again you can see the two consequences. If you plug those numbers into the equation, you get £0. That's the expected value in that case. And so this seems like a fair price. It looks like you're not being ripped off and your aunt isn't being ripped off. The expected value of getting the ticket for nothing is 90p, so you pay 90p for the ticket. 90p for the ticket is a fair price. Think of it from your aunt's perspective. For her, the lottery ticket is an asset. What is the value of the asset? Well, we've seen that it's 90p. So by charging 90p, she recoups her losses. The fair price of entering this lottery then is determined by the expected value of the ticket. And I mean, this is pretty intuitive, right? Imagine that the winnings were £900 rather than £90. Then you'd expect the price for the ticket to increase, perhaps to £9 rather than 90p. Another way to see that 90p is the fair price is to imagine buying every ticket. There are 100 tickets, so at 90p a ticket, you'd pay £90 for all 100 tickets. You would also be sure to have the winning ticket, which would give you £90 back. You'd break even. So the fair price of entering a game can be thought of as the expected value of entering the game for free. At least if we're just talking about it in purely monetary terms, that looks like the situation where both the person offering the game and the person entering the game, neither of them are getting ripped off. So, with all of this in mind, let's return to the St. Petersburg game. Here again is how the game works. Remember, if the coin lands heads the first time, the game ends and you get £2. If it lands tails and then heads, you get £4. If it lands tails, heads, you get £8, and so on. What would be a fair price to enter this game? Well, what's the expected value of entering the game? To work this out, we need to determine the probability of each consequence and the utility of each consequence. Obviously, I can't list all of the possible consequences because they are infinite. In principle, this game could continue indefinitely. But we can sort of work through a few of them, and that will still give us the answer. So one consequence is that the game ends on the first flip, so n equals 1. The probability of this is 1/2, right? I mean, assuming we've got a fair coin, the probability of landing heads is a half. The utility is £2. That's what you win. Suppose n equals 2, so I toss tails, then heads. The probability of this is 1/4, because the probability of tossing tails is a half, and then the probability of tossing heads is a half. So overall, the probability of tails, then heads is 1/4. The utility is £4. Suppose n equals 3, so that's tails, heads. This has a probability of 1/8 and a utility of £8. Similarly, suppose n equals 4, that's tails, heads. Probability of 1/16, the utility of £16. So we can continue this list indefinitely. We can sum this up as follows. We can say that S is the event that the game stops after the nth toss. The probability of S is 1/2 to the power of n. 1/2 to the power of 2. So this is a case of n equals 2. 1/2 to the power of 2 is 1/4. 1/2 to the power of 3 is 1/8, and so on. The utility of S is £2 to the power of n. So £2 to the power of 2 is £4, £2 to the power of 3 is £8, and so on. Now recall that to work out the expected value, we take the probability of consequence 1 multiplied by its utility, plus the probability of consequence 2 multiplied by its utility, plus the probability of consequence 3 multiplied by its utility, and so on. We take the sum of the products of the probabilities multiplied by the utilities. So, for n equals 1, we have a probability of 1/2 multiplied by a utility of £2, which is £1. For n equals 2, we have a probability of 1/4 multiplied by £4, which is £1. For n equals 3, probability of 1/8 multiplied by £8, which is £1. And it's the same for all the consequences. The probabilities multiplied by the utilities of each consequence gives us £1. So to get the expected value of entering the St. Petersburg game, we add all of these products together. £1 plus £1 plus £1 forever, and that means that the expected value of entering the game is infinite. And since, as we saw, a fair price is determined by the expected value, that means that the fair price is infinite as well. You should be prepared to pay any finite amount of money to enter the St. Petersburg game. In fact, any finite amount of money is a really good deal for entering this game. A rational gambler should play this game no matter how much the entry fee is. You should be willing to give up everything you have to play the St. Petersburg. It should be fairly obvious why this is a paradox. You would have to be crazy to pay even £30 to play this game. So let's look at some responses. Well, first of all, we might bite the bullet. We might say, okay, it's a strange result, but yes, in fact, a perfectly rational person would pay any amount to enter this game. Just because a theory has surprising consequences, it doesn't follow that the theory is wrong. Apparently, some people have taken this view. According to the Stanford Encyclopedia of Philosophy, Michael Clark says that, of the St. Petersburg, he says, this seems to be one of those paradoxes which we have to swallow. Now, I think that's obviously ridiculous. It would be insane to give up all your savings to play the St. Petersburg. I don't really know what else there is to say about that kind of solution, other than that anybody who buys this solution is more than welcome to pay me a whole lot of money, and I'll do the St. Petersburg for them. Of course, I'm kidding. I don't actually have an infinite amount of bankroll, so of course I couldn't really put it on. But you get the point. It seems like a pretty silly response. A second solution, one of the earliest solutions proposed, appeals to decreasing marginal utility. So far we've framed utility in purely monetary terms, but we need to distinguish utility from monetary amount, because not every pound is of the same value. If you give £100 to me, it will be of great benefit. £100 to Bill Gates won't even be spare change to him. It does nothing for him because he already has so much money. So we say that the marginal utility of Q given R is the utility of adding Q given that the person already has R. Now, the claim is that if we're talking about money, then for higher values of R, so the more money you have, the lower the value of Q. The marginal utility of £100 declines as you have more money. In the St. Petersburg game, if you win, each toss doubles your money, right? If you win at n plus 1, you get twice as much money as if you win at n. But this doesn't entail that you get twice as much utility. Indeed, it seems that the utility of each toss will diminish. Doubling your money is of less utility if you have £100 million than if you have just £100. If you have £100 million, you already have enough money for a lifetime of luxury. You'll never need to work again. You can basically do whatever you want. Doubling it won't really make a lot of difference to your life. On the other hand, of course, if you've just got £100 in the bank, then doubling it may well help quite a great deal. This allows us then to block the paradox, because the expected value of each consequence declines. So the expected value of entering the St. Petersburg is not infinite. This example is taken from the Stanford Encyclopedia of Philosophy. And what we find is that, in this case, the expected value approaches 6. So if the utility of each toss has this works in this kind of way, then we should pay about £6 to enter this game. Now, the main worry about this approach is that in order to keep the entry price reasonably low, we have to make the utilities decline extremely fast, far faster than would be acceptable. In this example, the utility stops increasing after we hit £32. So we'd be saying that £10,000 is of no more value than £32, which is obviously absurd. So this is just a toy example, but it kind of gives you a sense of just how quickly you're going to have to make the utilities decline in order to keep the entry price reasonably low. Now, obviously there are, as I say, different ways of working it out than I've done here in this toy example, but they all face this basic problem. You're not going to want to pay more than about £15 to enter the St. Petersburg. In fact, even £15 is probably too much, but you can't get the expected value anywhere near that low on a plausible model of the utilities. A third solution is to point out that the game just isn't realistic, because in the real world there are limits on how much money can actually be paid out. Nobody could actually give you trillions upon trillions of pounds. That kind of money doesn't exist. If we think about playing the St. Petersburg with a finite bankroll, so that you can't win more than the bankroll, then the expected value is of course finite. Wikipedia provides this list of the expected value of the St. Petersburg with different finite bankrolls, although I've converted it from dollars to pounds so that it's in line with the rest of the video. Bill Gates does not own £79 billion, it's $79 billion, but whatever. You get the point. So the other point, of course, is that even putting aside the necessary finitude of the bankroll, people will just run out of time. I mean, eventually you're just going to have to end the game because we don't live forever. So a run of tails must stop somewhere. So it can't just go on indefinitely. Now, I think the obvious retort to this solution is that it's really just changing the subject, right? It's not engaging with the paradox. Sure, the St. Petersburg couldn't be played in reality, but that's irrelevant. We can imagine the case of an infinite bankroll and ask what a rational person would do in those circumstances. It's perfectly reasonable to discuss what what should be done in hypothetical situations. That's an important way of testing theories of rational behaviour, to think about how we should behave in in hypothetical situations. But I think this retort is maybe a little bit too quick. Maybe it's not just that the St. Petersburg is impossible in practice. It might be incoherent even in principle. And this kind of gets to some of the trouble with thought experiments in philosophy, is that they can disguise incoherencies. We might not be fleshing out our imaginary scenario in enough detail. A number of philosophers, Dan Dennett, for example, are very wary of thought experiments for exactly this reason. We find that when we try to examine the thought experiment in detail, it breaks down when you try to flesh out the scenario. So, I mean, try to imagine actually playing the St. Petersburg. Suppose the government offered you the St. Petersburg. They can print money at will, so you have an indefinite supply. But at very large sums, printing money would create inflation, which would substantially reduce the value of the money that you get. I know there was a massive hyperinflation in Zimbabwe, and I think there was a situation where the average person had billions of whatever the currency is in Zimbabwe, I don't know. Let's say billions of pounds, right? They had billions of pounds, but it was worthless. You couldn't even buy a loaf of bread with it because of hyperinflation. So there is just necessarily an upper bound. Recall the point of the last response on diminishing marginal utility. The point that utility has to be distinguished from monetary value. It's the same point is being made here. Now, can you imagine a world in which there is no inflation? A world in which you can perpetually print money without running into problems? It's not at all clear that even in principle there could be such a system. It might just be built into the nature of economic systems that there is a limit to wealth. However, a second worry we might have about this kind of solution is that it's not clear that it works even on its own terms. Imagine that Bill Gates did offer to play the St. Petersburg with you. Why not? Maybe he's just bored. Would you pay, £37 to enter? That doesn't seem like a wise investment to me. In order to get a return on £37, you'd have to land 6 heads in a row. There's only a 1 in 64 chance of doing that. Even looking at it in terms of the finite bankrolls, there still seems to be a bit of a problem here. A fourth solution is that our analysis of the expected value of the St. Petersburg game hasn't built in an appropriate degree of risk aversion. So suppose I give you 2 choices. You can have box A, which definitely contains £10, or you can have box B, which has a 50% chance of containing £20. So do you take the sure thing £10 or the 50% chance of £20? It's clear that the standard procedure for working out expected value would put them at the same expected value. But we might think that this is wrong. Taking the £10 is a better choice because it has no risk of failure. We prefer certainty. We prefer the safer, secure options. Indeed, we might think that taking just £5 is better than taking a 50% chance of £20, even though the standard theory would say that the 50% chance of £20 is a higher expected value. And obviously, risk aversion becomes all the more powerful when you have to pay to enter a game. Putting up £1,000 to enter the St. Petersburg would be an incredible risk because you're very unlikely to make a return on your investment. Half the time you play the St. Petersburg, you'll only get £2. Even modestly high payments are very rare. It's just silly to gamble on a minuscule chance of winning a large prize. It's certainly silly to risk all your life savings on such a gamble. Now, this seems like it's probably along the right kind of lines, but there are a couple of worries about this response. First of all, one issue is that many people don't really seem to be all that risk averse. Many people enjoy risk, which is precisely why they enjoy gambling in the first place. Risk can be exciting, but it seems like nobody, not even the people who love risks, would gamble their life savings on the St. Petersburg. Of course, we might just explain this in terms of its being too risky, even for people who enjoy risks. After all, an adrenaline junkie might draw the line at playing Russian roulette with a bullet in 5 of the 6 chambers. Eventually the risks become too high. The second worry, though, about this response is that it doesn't really solve the whole paradox. We might say that there are really 2 paradoxes in the St. Petersburg. One is that it seems to show that it's not always rational to maximise expected value. Paying £1 million to enter the game would maximise expected value, but no rational person would do that. So how do we explain this discrepancy? That's one question. But the other paradox is that the expected value of the St. Petersburg game is infinite. Risk aversion may well tell us why it's not rational to maximise expected value, but it doesn't address this other aspect. I mean, if we want to show that it's not always rational to maximise expected value, there are other examples we can use. Suppose there is a lottery ticket with a 1 in a million chance of winning, but you can win £20 billion. What should you pay for the ticket? Well, the expected value is very, very high. It's probably something like £20,000. So would you pay £20,000 for that ticket? Surely no rational person would pay such a price. I wouldn't even pay £100 for that ticket. We might appeal to risk aversion to explain cases like this. I mean, there's only a 1 in a million chance of winning. It's just not worth it. But clearly there's something more going on with the St. Petersburg, and that's this way it ends up with infinite expected value. So perhaps, so those are some solutions, some possible solutions. Perhaps the right way is to look for combinations of solutions. For example, a combination of solution 3 and 4 might work. Solution 3 is what blocks the derivation of infinite expected value. And then solution 4, risk aversion, tells us why even with a finite bankroll you shouldn't pay, because it's just too risky. So, that's the St. Petersburg Paradox. I hope you found that interesting. That's all for today. Goodbye.